Hey everybody, today I'm coming at you with a brand new setup. So I got some different lighting and it's a lot better in my opinion so far, so we'll see how it works. I've rearranged my whole room, so I'm in a different side of my room. Now I'm against an actual flat wall. This whole time I was against a curved wall, and it wasn't, it wasn't great, but I dealt with it. But now we have, honestly, this is much better, and I'm really happy that it turned out to be this way. So yeah, we're gonna have my first video with our new setup on absolute value. And you might be like, well, absolute value is pretty easy. Absolute value is just, if you take the absolute value of x, this is just either x or negative x, right? It's x if your original number x was positive, or 0. Well, actually, that's another thing. Hold on. And it's negative x if x is less than 0. And also, it is 0. I'm sorry. Yeah, 0 if x is equal to 0. Right? Really, this could fit into any of these if you made this equal to or whatever, but these are the three, if you put them in actual order, these are the three kind of, it's like a piecewise definition of absolute value. And this is actually a satisfactory definition if this is all you're looking for, right? You know that if you take the absolute value of a number, if that number is positive, it's going to stay positive. If it's negative, then your absolute value of it is going to still be, you're going to take the negative of that negative number, so it's going to be a positive number. And if it's 0, it's just 0 still. So this is how we define absolute value. There are many different ways to do it, but really what I want to bring to you guys today is talk about how absolute value is a distance function. All right, it's a distance function. I'll just put it down here. This is the idea I really want to emphasize today. You might be like, oh yeah, I already know that. I mean, I already know the whole video. Not quite. I'm going to generalize the idea of distance functions to something more abstract called metric spaces. So this is the whole idea that I'm going to talk about today. And if you're not familiar with metric spaces, they're actually super cool, super useful, and they're really real world. They're super applicable to the real world. And I'll talk about those in a second. They connect a lot with topology, which I've made a video on. And I'll probably make a couple of videos in the future on topology. I'm just not super interested in making a whole series on it. I just want to, we'll see how that goes. But yeah, this connects a lot with topology. And I'll show that a little bit in this video. But yeah, so let's say, what is a metric space? So a metric space is a space with a metric. Okay, well, what's a metric? Well, a metric is just a distance function. So this is just a metric. It's another name for a distance function. That's really all it is. So the way we talk about metric spaces is we have the set. So typically it's a set capital X, and then we do a comma, our distance function, which is typically denoted as a lowercase d, alright? So absolute value is the metric on the real number line, okay? The one-dimensional real number line. We'll talk about multiple dimensions in a second, but for our real line, we have r, and you can put an r1, not r prime, that's an r1 for one dimension, but really if people see this, they typically know it's just the one-dimensional real line, or Euclidean line, whatever, with its distance function. And here, the distance function, so let's see, I actually don't want to go into this now because first I want to talk about the axioms. But actually, let me just write it down. So the distance between x and y, which is 2 points, is equal to the absolute value of x minus y, or the absolute value of y minus x. It's not going to matter, and I'm going to show you why in a second. So let's talk about the axioms. It's always good to start with some axioms of what even a metric space is, because when you say a distance function, it's like, all right, well, what is distance? So we're going to define how a distance should be talked about basically. So first off, a distance function, our distance function should, for any metric space, between, let's say, so the distance between any two elements, x and y, so I'm going to say, we're going to say that x and y, and I think we'll use a z in the future. These are all in our big set capital X for any metric space. It's just really, like, if the way you think about this is x is just some normal set, any set that you choose, and then d, the distance function combined with this set, makes your metric space. So this set really is just any ordinary set. When you combine it with the metric, it forms this whole metric space. So that's basically how you should think about it. So these are just elements of a set. That's really all they are. So the distance between x and y must be in the interval 0 to infinity, including 0. Let me actually make that a little clearer. So what I'm saying here is that the distance between two objects must be a positive number or 0, okay? I'll talk about that 0 case in a second. And it shouldn't include infinity, but like, it should be just some positive number. Or another thing you can say is that the distance between any two things is in the, sometimes it's denoted like this, the non-negative real numbers. So this is greater than or equal to 0. I personally prefer something like this. I don't really like writing this much, but you totally can if you want to. So we're saying that the distance between any two things should be a positive number. So what that really tells us is that the distance between x and y is going to be equal to the distance between y and x. So if I go from here to here, that should be the exact same as going from here to here. Sure, you went the other way, but remember, like, we're saying that it has to be a positive number. So it doesn't matter which way you go. There is no, like, preferred direction. They're the same thing, all right? So now let's talk about that 0 case. So for something to have a distance of 0, or for two things to have a distance of 0, so for, like, two objects to not have any distance, they have to be the same object, right? They have to be in the same location. So that tells us that the distance between x and another x, and itself basically, is equal to 0. And that also basically tells us that the distance between x and y, if that is not equal to 0, that implies that x is not equal to y. Let me make that implication error a little neater. Alright, so that tells us, so if the distance between two objects is not 0, that means there is some distance between them, and again, it has to be positive. If it's not 0, it has to be positive. So if there is a distance between any two objects, that tells us that those two objects are not in the same location. They're not the same. So that's that. And also, it works the other way around. It also works the other way around. If you have the distance between, if you have two elements, x and y, and we're saying that they're not the same, they're going to have a distance. So it actually goes this way as well. So it's an if and only if statement. Okay, so there are, I think there's just one more axiom that we have to cover. Let me just make sure. Because I don't believe that, hold on, where did I put it? Yeah, there's just one more axiom. And this is known as the Triangle Inequality. So let me just write it out first. So the distance between x and z, this is what we were talking about. Let me just put it this way. Distance between x and y is less than or equal to distance between x and z plus the distance between z and y. Alright, so let me draw it out as a picture. So let's say we have a point x here and a point y, so we're dealing with two-dimensional space, right? X and y. Their distance, let me just make it better. I tried, but it's okay. Alright, so yeah, we have x and y here, and this is going to be the shortest possible distance, alright? Any other distance is going to be either equal to or longer. So let's say we have another point z over here, right? And instead of going between x and y, we start by going from x to z, and then from z to y. So the distance from x to z, plus the distance from z to y, right? This is obviously, when z is over here, or really anywhere that's not on the line, when z is pretty much in most places, this is going to be a less than. So this, between x and y, it's going to be less than from x to z and then from z to y. Now, I have this equal down here. It's less than or equal to. When would it be equal to? Well, that's actually pretty simple. If z is instead on here, on the line, the distance between x and z and then from z to y, it's the exact same as going from x to y. Like, you can think about going from, I don't know, California to New Mexico, right? If you go from California directly to New Mexico, it's the exact same as going from California to Arizona, then Arizona to New Mexico. Of course, as long as you don't like take any detours or whatever. If you go the same route but then stop halfway through, you're not gonna. It's not gonna matter. Like, yeah, there's more time, but we're not really concerned with time here. We're concerned with distance. Okay. There's like the calculus of variations, I believe. That's where you're concerned about like minimizing the amount of time or whatever spent on a journey. That's interesting in itself. There's a very interesting video on it. I'll link it if I remember. But yeah, we're not concerned with that. We're concerned with distance. Okay, so this is known as the triangle inequality, and I'm gonna actually write this down. I should have erased that because it's called the triangle inequality because of how it looks. You remember, you have the x and the y and then the z down here, so that's a triangle. So that's why it's called the triangle inequality. So triangle inequality. So I want to generalize the triangle inequality a little bit because you know how like you could go between multiple points, right? So if you have x and y here, and instead you wanted to go not between x and y, but then you have a z, and then maybe you have a w over here. So then you would just go like here. Let me actually draw a straight line. Oh, that's a mess. Yeah, so you go there, and you go up here, and then you go here. This, again, is going to be longer, but remember, you have multiple points. Maybe you have another point here, and then another point here, and whatever, you know? So you could have a finite or even an infinite amount of points. Actually, I don't know about infinity, but definitely you can have a large number of points between here, right? That satisfies this. So in general, let's say we had the distance between x1 and xn, right? So we had a point x1 here and a point xn, right? So let me just draw a dotted line, so because it's whatever. So maybe instead of just going on the straight path, we stopped at a point x2 and then x3 and x4, x5, x6, x7, x8 all over here, x9 and then xn, whatever. So this, again, is going to be less than or equal to, if all the points are on the line, the sum, right? So we're going to be summing up all of the distances, and I'll say this is n, so we have xn to xn plus 1, right? So n starts at 1, right? So n is going to start at 1, and it's not going to go to, I'm sorry. I shouldn't use the same one. I'm going to use I instead. So I. So x goes from I to I plus 1 from our index, right? So it's going to start at 1 and it's going to end at n minus 1. There we go. Yeah. Why does it not end at xn? Or at n, just n right here? Because then you're going to be taking, if you had n, if you plugged in n for I, you would have the distance between xn and xn plus 1. Well, we don't have an xn plus 1, so we have to stop at the xn minus 1, comma xn. So that's just the explanation. But yeah, this is true. This is generalizing the triangle inequality. if you have more than just 2 points. Now, one thing I want to talk about with this plus, if you're interested at all in any like group theory or whatever, you might be like, whoa, what if our set doesn't have addition? What if it has a different operation? Well, yeah, that's going to be a little more troublesome there, because that's, you have to define distance and all that, but distance doesn't really have any relation to, metric spaces don't really have much of a relation to groups and group theory. I'm sure there's a connection, but there isn't really like it's probably too advanced for this video, but yeah, so we're not going to talk about group theory and the operations here, because really this addition just works for the real numbers, and really any set where you have addition defined, well, we're not really concerned with that. What we are concerned with is topology, because essentially, let me try to get this right. So a metric space has a topology. Yeah, a metric space has a topology, but a topology does not always have a metric space. A topological space does not have a metric always. It can. If it does, then it's called a Hausdorff metric space, or a Hausdorff topological space. So a Hausdorff topological space. So this one it's a topological space with a metric, all right? If it doesn't have a metric, then obviously it's not that. But in general, topological spaces don't always have a metric. Metric spaces always have a topology defined on them. So that's the connection between topologies and metrics. But yeah, so these are the axioms, and I just wanted to make this video to really just make sense of these axioms. And yeah, the absolute value does actually fulfill these. This is easy to see. Absolute value is always, if you just look at the graph of the absolute value, it's always positive. Like the codomain or the range is always positive. So it definitely fulfills this first one. The second one, you know that it fulfills because if you do, x minus y, or the absolute value of y minus x, it's the exact same thing. Distance between x and x is 0, makes sense. The distance between x and y, okay, that also makes sense. The last one, the triangle inequality, that's not like immediately obvious, but you can definitely show that for yourself. You're going to use a lot of absolute values and all that. But one last thing I want to talk about is, because this is just one-dimensional space, right? Because what we're saying is we have the real number line with 0 here going off to infinity, right? This is the real number line. And then we have some point x here, and maybe we have some point y over here, right? And we're talking about the distance between these two guys. What if we want to talk about 2 dimensions, right? So, so I'm going to erase the board, and we're going to talk about 2-dimensional and higher dimensional, basically absolute value, the real metrics for higher dimensions. Okay, so now we're going to talk about really distance in Euclidean n space, where Euclidean space is really just the real space. It's another name for it, and n is the number of dimensions we have. We were dealing with Euclidean 1 space because we were dealing in 1 dimensions. Now let's think about 2 dimensions. Well, we know that we have the distance formula, right? So we can say that the distance, so actually, before I say that, we have to define the actual space we're on. So we are on the real numbers in 2 dimensions, and we have a distance function. And that distance function is going to be distance between x and y. Alright, so these are 2 points. Actually, I don't want to use x and y because that's going to be confusing with the coordinates. So I'll say a and b. Alright, so the distance between a and b, right? Now, you might be like, okay, well, a and b, like if we're dealing with 2 dimensions here, let's say a is over here, and then b is over here, right? Their distance is going to be this straight line. So a has an x and a y coordinate, right? So a really is just a1, comma a2. And then b is just b1, comma b2. Where a1 and b1 is your x coordinates of that particular point, and a2 and b2 are your y coordinates of that particular point. You could do ax, comma ay, and bx, comma by if that really helps you. just so you can keep track of what each coordinate means. But yeah, so that's how we're going to define these. So this is going to be the distance formula, which really is just the Pythagorean theorem, right? So basically we're going to have that absolute value, right? And we're going to start off with, first we need the difference between the two x coordinates or the two y coordinates. Really doesn't matter. We're going to start with the x coordinates. So it's going to be b1 minus a1, or again, a1 minus b1. It doesn't matter because you're squaring it, and when you square something, it's always going to be positive anyway. And then we're going to say plus, and we have b2 minus a2, square that, and then we're going to finish off the square root, right? This is our distance formula between a and b, or b and a, and again, it looks like this, right? In 3 dimensions, we have a very similar formula, and again, we're not just going to have two things added. We're going to have this, the x coordinates, plus the y coordinates, plus the z coordinates, right? So the differences squared of each of those. So let me actually show you. So for the real line in 3 dimensions, our distance between a and b, right? So this is just going to be, it's going to be a lot longer. So start off with the square root, and then we're going to have b1 minus a1 squared plus b2 minus a2 squared plus b3 minus a3 squared. And it's going to be the square root of all of that, right? So these are our x's, our y's, and our z's, right? So in general, if we're dealing with Euclidean n space, the distance formula is really actually very easy. So the distance between 2 points A and B in n dimensions, so this could be 20 dimensions, a million dimensions, it really doesn't matter. So we're going to start off with the square root, and then we're going to sum up a bunch of things. So we're going to sum up. So we always have like the b1 minus a1, so we're going to have a b, I'll say I, minus ai, where again I is not this imaginary unit, it's just an index, and so I is going to range from 1 to n minus 1, n minus 1 again for the same reason as before, and so we're going to take the square root of all of those. And so this is the general distance formula for something in n dimensions, and you can test it. Okay, if you have I going from 1 to 2, right, essentially this is going to be your x components plus your y components, right? So that would be in 2 dimensions. You can test it for as many dimensions as you really want. But yeah, actually no, this goes to n, not n minus 1, because you want to have that bn minus an. Sorry if that was confusing. But yeah, you're going to go up to n because it's the number of dimensions, and you have one term for each dimension, right? So you have your first dimension here, second, third, fourth, all the way to your nth dimension, whatever that may be. So you have one term for each dimension. Add those up, take this, you do the whole thing by subtracting off the differences here, squaring it, add all of those up, and then you take the square root, and that is your distance. Now, there are other distance functions. One popular one that I really like is the Taxicab Metric, right? The Taxicab Metric is really interesting because think of a city, like New York City or whatever, and you have, you know, these roads, right? Like this is a city, like the roads in a city. Let's say you want to go from here to, I don't know, over here, right? So you can only travel on these lines. So maybe you start off here, then you go up here, or maybe, so this seems to be like the shortest path. Another equivalent shortest path, which is just basically there, or you can start off here and go this way. There are a few different equivalent short paths, but yeah, then you could also go on some crazy paths. You can go all the way up here, like that maybe. It really, like, there are different ways to go there. There is a shortest path, and in this case there are a few different shortest paths, but they actually get you to the same place. So yeah, this is the Taxicab metric. It's another type of metric. And there are many different types of metrics. I encourage you to check them out. Just look up metric spaces examples, I guess, on Google or YouTube, and you should be able to find some cool ones. Some make more sense than others. But yeah, there are many different ways. You can actually define the distance between two functions. I could make a video on that. That could be interesting. But yeah, just let me know if you guys want me to make any more videos on metric spaces. I really enjoyed this. I'm going to be making a follow-up or kind of a follow-up video on absolute value at some point in the future, with more of its calculus applications and like taking the derivative of absolute value, you know, working with absolute value with integrals and derivatives, all that kind of stuff. So yeah, sorry this video's been long, but I hope you enjoyed. Thank y'all for watching, and I'll see you in the next video. Bye guys.